bring the water back, and the land heals. That is the promise behind almost every climate plan on Earth right now. Flood the drained marsh. Let the peat soak. Lock the carbon back into the mud it came from. Nobody tells you what the ground does next. It starts breathing out a gas that traps heat far better than carbon dioxide does. More than 5 times as much of it as before you helped. In the next few minutes, you will find out why flooding a field turns ordinary soil into a factory for the gas that is climbing fastest. Why dry ground does the opposite and quietly eats that same gas out of the air. Why the ledger's governments report their emissions with carry a number here that is simply wrong. And why a restored wetland has to make things worse before it becomes one of the best things you can do. Think of the last marsh you walked past. Flat brown water. Reeds standing in it. That smell. Under the surface, something is working its way up through the mud in small bubbles and popping quietly at the top. Watch long enough and you can count them. Each bubble is a small parcel of heat leaving the ground for the sky. So how can a place that does this be the thing we are told will save us? In the autumn of 1776, a man was wading through the shallows of a lake in northern Italy, poking at the bottom with a stick. Every time he stirred the mud, the water fizzed. He held an upturned jar over the bubbles until it filled, then put a flame to it. It caught. The jar burned with a pale blue flame. That was the first time anyone had isolated methane, and he found it in a swamp. The man was Alessandro Volta, and the Volt is named after him. He called it the flammable air of the marshes. Marshes had been making that air for millions of years. Farmers called it swamp gas. Travelers blamed the pale lights flickering over the bogs at night on ghosts. All of them were watching one kind of microbe at work. Scientists call them methanogens, methane makers. They live buried in airless mud and they exhale the same gas that comes out of your kitchen burner. Now walk 20 steps up the bank onto dry ground. Completely different world. This soil is full of air, and air is poison to a methane maker. What lives here is the opposite creature. Methanotrophs, methane eaters. They pull the gas out of the air that seeps down into the soil and burn it to stay alive. A dry meadow is not failing to release methane. It is quietly removing it. 2 teams of microbes. The same planet. One filling the sky with heat and one taking it back out. So what decides which team gets your patch of ground? One thing decides it. The height of the water. Dig a hole at the beach, and at some depth the bottom starts filling in on its own. That line where soil stops holding air and starts holding water has a name. The water table. Raise it, and the air is pushed out, and the makers take over. Drop it, and the eaters take the field. It is the closest thing soil has to a switch. Everything else about a marsh can stay as it was. The plants, the temperature, the mud itself. Move that one line up or down by a few centimeters, and the ground changes which gas it hands to the sky. Which matters more than it sounds, because for 300 years we have been pushing that line down on purpose. Wetlands were not treasured. They were sick ground where the fever came from, and where nothing useful grew. So we cut ditches and built pumps and windmills, until the map of Europe changed shape. In 1851, somebody in the east of England drove an iron post through the peat until its top sat level with the ground to see whether the draining was doing anything. The post is still standing. The ground around it has dropped about 4 meters. You can stand at the bottom now and look up at a first-floor window of empty air. That missing ground did not wash away. It burned, slowly and invisibly and without a flame. Once air reaches drained peat, the carbon locked in there for thousands of years combines with oxygen and drifts off as carbon dioxide. Drain a bog and you have lit a bonfire that takes a century to finish. That is why these places matter far beyond their size. Wetlands cover less than 1/10 of the land on Earth. They hold close to a quarter of all the carbon in the world's soil. No other ground comes near that ratio. Which is why the plan now is to put the water back. The United Nations has named this the Decade of Restoration, and the target is 1 billion hectares of land brought back to life. That is more ground than the entire United States, much of it wet. So we are about to flip that switch the other way on purpose across an area the size of a continent. And this is where the usual explanation goes wrong. You have heard that wetlands are the planet's greatest carbon sinks and that bringing them back is the cleanest win in climate policy. That sentence is convenient. It is also incomplete. The moment the water rises, the makers wake up. Which leaves the question this entire story hangs on. Is a restored marsh cooling the planet or heating it? To answer that, you need a way to compare gases that behave nothing alike. There is one, and it has a name: global warming potential. It is an exchange rate. It tells you how much heat a kilogram of a gas traps compared with a kilogram of carbon dioxide over 100 years. On that scale, carbon dioxide is 1. Methane is about 30. The gas that rises off fertilized soil is closer to 300. But the exchange rate hides something. Methane is a blowtorch. It burns hot and it is gone from the air within a decade. Carbon dioxide is an ember, feeble by comparison and still glowing centuries from now. So a restored marsh does two things at once. It lights the blowtorch immediately, and it starts smothering embers that would have glowed for hundreds of years. Add that up over 1 year, and the marsh looks like a catastrophe. Add it up over a century, and the arithmetic turns completely around. And methane is not a small side story. There is roughly 2.5 times more of it in the air today than before the factories. Carbon dioxide over the same stretch went up by about half. You already live beside one of these methane factories, even if you have never set foot in a bog. A flooded rice field is a wetland we dug on purpose. The same shallow water, the same airless mud, the same microbes at work. Rice feeds more people than any other crop on Earth, and every field of it bubbles like the marsh. If you enjoy watching a comfortable climate story get complicated by the actual measurements, subscribe. We dig one of these up every week. Now back to the question nobody had properly answered. So why does anyone still recommend flooding the ground? Because of what the mud does after the first few years. Every restored piece of land goes through a stage that deserves a name. Call it the switchover. It is the moment the ground stops giving off more carbon than it takes in and starts doing the reverse. Before it, the site is a source. After it, the site is a sink. Think of a bakery that loses money through its first 2 winters and then never looks back. Same shape. The ground opens in the red and pays you back for the rest of the century. Nobody had a solid number for how long those red years last. There is a place that shows why the waiting matters. In the early 90s, the marshes of southern Iraq were deliberately drained to punish the people living in them. An expanse of reed and water the size of whales turned to salt and dust. After 2003, the people driven out broke the embankments themselves, and the water came backments themselves, and the water came back. Within a few years, there were fish and buffalo and birds again. But nobody on that bank was measuring what the mud was doing to the atmosphere. The wildlife came back long before the accounting did. For years, the answer depended on which site you happened to visit. One re-wetted bog would be pouring out methane. Another would be quietly banking carbon. Both were true about their own patch of ground, and neither could tell you what was happening to the planet. And the ledger's countries report their emissions with barely had a page on any of it. When a nation floods a drained field, it has to write a number down for each gas. For one of them, the guideline said 0. 0 is a very strong claim about ground nobody had measured. So what happens if you gather every one of those contradictory sites and put them in a single pile? That is finally what somebody did. More than 250 separate field studies were pulled together, Nearly 700 matched pairs of ground. Each pair is a restored site sitting right beside the unrestored ground it used to be. Same weather, same soil. One difference between them. The methane coming off the restored wetlands went up more than 5 times over, not 5%, more than 5 times, from a trickle to a steady stream. Now the strange part. Do the same restoration work on a forest, and the ground goes the other way entirely. Restored forest soil pulls in nearly twice as much methane as before. Restored grassland pulls in about 1/3 more. The same instinct to heal the land and the opposite result in the air. Line the 3 of them up and you get a ranking almost nobody expects. Forests first by a distance, grasslands behind them. And in last place by an enormous margin sits the ecosystem everyone calls the champion of carbon storage. The reason is the switch we already met. Trees drink hard and dry the soil out, and air reaches down to where the eaters live. Flooding does the reverse and hands the ground to the makers. Restoration is not one thing. It is whatever the water table decides it is. Then the second gas. The one worth close to 300 times as much heat as carbon dioxide. Restored wetlands cut it by about 2/3, and that is the gas the guidelines had written down as 0. Measured properly, it comes out around 2 kilos per hectare every year. Small on its own, not nothing. Put all 3 gases together with the exchange rate, and the restored wetlands still come out ahead. Their total warming effect falls by roughly 2/3 against the drained ground they replaced. The blowtorch is real. The embers it puts out are simply bigger. And the switchover finally has numbers on it. A re-wetted wetland takes about 4 years to stop being a source and turn into a sink. A newly planted forest takes 3 to 5. A forest growing back from fire takes more than a decade. The methane spike does not last forever either. It climbs, holds, and settles about 10 years in. Some re-wetted bogs are indistinguishable from wild ones by 15. Restoration is not a permanent tax. It is a bill that is heaviest at the beginning. One honest limit. This is hundreds of field measurements from wildly different places stacked together, not a controlled experiment on one patch of ground. It gives you the direction and the rough size of the effect. It cannot tell you what your local marsh will do next spring. So the next time somebody tells you that bringing nature back is a straightforward win for the climate, you know what to ask. Which gas? Measured over how long? Because the ground you fix will make things worse before it makes them better. And that is not a reason to leave it broken. That is what the targets keep missing. The fastest climate fix and the best climate fix are almost never the same thing, and the distance between them is measured in patience. The marsh will pay back everything it borrows. It just keeps its own books, and it settles up on its own schedule.